Light on. Red. White. Light off. This ESP32 listens to me. No internet, no cloud, just straight up AI running locally on the chip. Want to give this a shot yourself, even if you've never worked with machine learning before? With Edge Impulse you can make your own machine learning models for almost any small device, for free. And don't worry, Eric, my little AI assistant, will guide you through step by step.
Hi folks! Let's jump right in and create a keyword classification model for the ESP32. Their examples page is a great place to start. To get there, open their online documentation page. In its sidebar, click on Data, then Edge Impulse Datasets. There you'll find lots of example projects to get started with. For our case, pick Keyword Spotting to open the project description page. This example detects the phrase, "Hello World." Scroll down and click the Clone the Public Project link. This takes you to the project itself, where you hit the button at the top right. If you haven't already, you'll need to log in or sign up for free. Then, just name your project whatever you like, or keep its default name. You can keep it either private or make it public. This shares it on the Project Hub, where there are tons of other cool projects you can clone. Maybe one day you'll want to build the perfect toast machine.
Perfect toast machine. That sounds funny.
Of course, I'm keeping it private for now. Once cloning's done, click the top right button again. This time you'll see a list of supported development boards. I'm choosing the ESPI. This is basically an ESP32 module with a camera, a digital microphone, and a red and a white onboard LED. Alright, let's move on and check out the training dataset from the project we just imported. Click on Data Acquisition in the sidebar to open it. We've got about 34 minutes of speech data split into 1-second snippets. There are 3 categories, or labels. Unknown, which means words or phrases other than Hello World itself, and background noise. We're going to use 80% of that data to train the model and the other 20% to test how well it performs. Let's take a listen.
Hello World. Backward. Hello World.
All these chunks were recorded with different voices to make the model as robust as possible. By clicking the little funnel icon, we can filter for the labels we want to see. I'm filtering for Hello World to show only those samples. Then I click the checkbox icon and check Select All. We want the ESP to detect red and white instead, so we don't need the Hello World samples, and I can safely delete them. Now you can easily record your own audio samples. Clicking the link opens a dialog with 3 options. First, you can use your dev board for recording. This requires flashing special firmware and running the Edge Impulse Data Forwarder on the command line. But when I tried this, it either recorded only noise or didn't work at all. The second option is to use a web browser, which opens a new tab where you simply allow access to your microphone. Click here to enter the label of the sample data. I choose white, like the word that I want to record. Then click here to set the recording length, 10 seconds for example. Finally, choose how this data should be used. By default, it's split 80% for training and 20% for testing. But you can also set it to use all of it for either training or testing only. Then you're ready for recording.
White, 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 white.
The QR code on the left links to a mobile version of this page. Just scan it with your phone to open it. You can then use your phone's microphone to record your audio samples. No matter how you actually recorded your audio, it'll show up in the dataset automatically.
White, 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 white.
Click the 3 vertical dots and open what I call the Split Editor. Here, you can break your recording into small 1-second segments.
White,
To get rid of background noise like that little crack, you can move the segments around like so.
Right.
You can also delete bad segments or add new ones. Then click Split, and once all the segments are created, the new samples show up in the dataset.
Right. Oh, that sounds like a lot of effort. It feels a bit awkward to ask random people on the street to say red and white into my phone.
Of course, you can also record just your own voice. Then the ESP will only respond to you or people with voices very similar to yours. In some cases, that might even make sense. But luckily, you can also generate synthetic training data. To do that, open the Synthetic Data tab and pick from different image and audio sources. For this project, we need OpenAI's Whisper Synthetic Voice Generator, so I choose that one. For access, you'll need an API key, which you can easily create in your OpenAI account. For this, go to openai.com and sign into the API platform with your preferred login method. Then open the Settings page and navigate to API Keys. Click on Create a new secret key. Then copy your key and paste it into Edge Impulse. Then you enter the word or phrase you want it to say along with the matching label. I recommend generating about 600 samples, around 10 minutes of speech, using random voices. You can keep all the other settings at their defaults. Now the generation can begin. This takes a few minutes.
Phew, I need a quick break. But let's not waste time. Let's talk about the sponsor of this video, PCBWay. Instead of assembling your circuits on messy breadboards, simply send them your Gerber files directly from KiCad via their plugin, specify your requirements, and a few days later, the boards will arrive. I love the high quality PCBs, and that's why I love to work with PCBWay. Soldering is always fun and done in no time, even for beginners. And PCBWay not only makes PCBs, they do also offer CNC machining, sheet metal works, 3D printing and injection molding. Get everything you need for your awesome projects from one hand, so give them a try. Now back to the topic.
Alright, here's the complete dataset with 4 labels. I did also prepare some samples for the word red off camera. Now we need to create an impulse. An impulse is basically a machine learning pipeline customized for specific tasks, like our keyword recognition. It has 2 parts, processing blocks and learning blocks. Processing blocks do some crazy math on the input data to get it into shape for the next step, which is done by the learning block. Learning blocks are the neural networks that do the actual AI work. To add a processing block, click here. And from the pop-up menu, pick the option that best matches your task. The MFCC is great for human voice, so I take this one. Then we also need a learning block. Since we're classifying audio into red, white, unknown, and noise, we'll add a classification block here. Don't forget to save the impulse afterwards. Now the blocks show up as 2 new entries in the sidebar, the processing block and the learning block. Let's look at the MFCC processing block now. MFCC stands for Mel Frequency Cepstral Coefficients. This process slices the audio into small windows of about 20 milliseconds. Then it runs an FFT to get the frequency spectrum, normalizes everything, and applies some fancy math until we get the so-called cepstral coefficients. These are arranged in a matrix like the one we see here. You can think of these matrices as images of the audio. They serve as the input values for the classifier. These are the parameters used for the process. I won't go through each one in detail. There's a handy auto-tune feature, so I click it and it automatically finds the best parameters for our dataset. This can take a bit, so hang on. Okay, it increased the frame length to 25 milliseconds, which reduces the size of the feature matrix. It also set the low frequency border to 80 Hz, roughly the lower limit of the human voice and basic microphones. The high limit stays at half the sample rate. For the ESPI, that's 16 kHz divided by 2. Now I just need to save the parameters, hit Generate Features, and wait a few minutes again. When this finishes, we get to the Feature Explorer. Here, our samples are shown as dots, each class in its own color. Samples with similar features are placed next to each other, forming clusters of the 4 classes. You can immediately see that red and white are clearly separated, while there's less separation between noise and unknown. This process is pretty time-consuming. On the ESP32, feature extraction takes a bit more than half a second. Okay, now we're ready to train our classifier. Here we can adjust some training parameters to fine-tune the results. And this checkbox here enables the Learned Optimizer, a neural network designed to train other neural networks, basically an AI that trains other AIs. However, this really only makes sense for large models, not small ones like our keyword classifier. In our example, training took much longer and the results were actually worse, so I'm leaving the settings as they are. Running the training on a GPU instead of the CPU cuts the time from about 2.5 minutes to just over 1 minute. But with small models and datasets, there's no real benefit. Their GPU pool is also limited, so sometimes none are free. In that case, you can either wait and try again later, or stick with the CPU. Another handy feature is data augmentation. It lets you add noise to your training data or mask parts of the spectrum. This can be useful if you plan to use the model in a noisy environment. But in my quiet lab, I got the best results by leaving it off. Next is the architecture of our neural network. It takes the feature matrices created in the MFCC process and distills them into our 4 classes: white, unknown, red, and noise. If you're an expert, you can tweak the properties of the individual layers, or rearrange them. Add new ones. And of course, delete layers that you do not need. All right, let's start the training. After it's finished, we can see how well the model performs. The accuracy value shows the percentage of test data predicted correctly. Specifically, all the white samples were classified right, but only 102 out of 104 red ones. These values are quite good. If we scroll down further, we come to the Data Explorer with more details. Here we see the clusters of our 4 classes again. The reds and whites are well separated, which is exactly what we want. The red dots in between show the misclassified samples. To check the incorrect reds, I click on the noise and unknown classes in the legend to hide them. Then I zoom in with the mouse wheel and select one of the red points to listen to it.
Red.
You can see that this one was mistakenly predicted as unknown. Let's also try the other one.
Red. These are samples that were spoken by me.
Well, you can record more samples to help the model adapt better to your unique accent.
That's a polite way of saying terrible accent. At least all 50 of my whites were recognized correctly. But now let's get back to the topic. Can you talk about the on-device performance, please?
Sure. There's not much to say. The inference time is around 10 milliseconds on the ESP32, so the model runs pretty fast. RAM usage is just a few kilobytes, and the model needs only 31 kilobytes of flash memory. That's it for this part. The model is ready to use now.
Awesome! I can't wait!
Wait a minute. I recommend testing it first. You can do this easily with live classification, which lets you try the model online and see how it will work later on the device. Click on that little bug icon, and the same list of recording devices pops up as the one we used earlier when recording the training data. Again, I choose my computer since it's the most convenient option. Then the data collection page opens. This time, switch it to classification mode and grant access to your microphone. Give it a try.
White.
The numbers you see here are the probabilities for each class. The closer they are to 1, the more confidently the corresponding keyword has been detected.
Red.
Later, when we implement this in the ESP32 program, we'll need to set a threshold value above which the program will treat the word as detected.
Green.
If this threshold is set too low, the program might confuse different words.
Unknown.
If it's too high, it could miss valid ones.
Red.
Here, 0.9 looks like a good balance. If we're not happy with the outcome, we can gather more training data by reloading the page and switching to data collection mode. Then we can start recording additional training and test data.
Red.
When we're done, we split it into 1-second pieces. just like we did before. With the new samples in place, the little red dot here shows that the model is ready to be retrained with the updated data. So let's do it. Back in the classifier, we can now see that red was recognized correctly for all 111 test samples. Looking at the Data Explorer below, there are no misclassified reds anymore, just a few mismatched noise or unknowns, which I'm not worried about. This shows the model is now perfectly tuned to my master's voice.
Yeah, that sounds useful. But now let's come to an end as the video is already getting too long.
Okay, boss. I'll skip the next two optional steps in the workflow: model testing and performance calibration. The latter adds some post-processing to further optimize the model, but it didn't work for me. So instead, I'll go straight to deployment. By default, the model is deployed as a plain C++ library that works with any modern compiler. But there are other options too. I'm choosing to deploy it as an Arduino library. The EON compiler, short for Edge Optimized Neural Compiler, significantly reduces memory use and speeds up inference, while maintaining the same accuracy, ideal for low-memory edge devices. Another option is exporting the model using TensorFlow Lite, a lightweight framework for machine learning on mobile or embedded platforms. But for this project, I'm sticking with the EON compiler, as it appears to be the better fit. Last, we can choose to export the model with either quantized 8-bit integer weights or standard 32-bit floating point weights. Quantized models run faster, use less memory, and may even perform slightly better in terms of accuracy. With these settings, we can now start the build, which exports everything into a zip file. It takes a little while, but once it's done, we can save it. A brief guide also pops up showing how to use the library with the Arduino IDE. There, we can import this library. But before that, make sure you've installed the ESP32 platform files from Espressif using the Platform Manager. Then go to Sketch, include library, add zip library, and select the zip file you exported earlier. Under Files, Examples, we now find some demos for our library across different platforms. Under ESP32, I pick the microphone continuous example since it runs faster than the other one. There it is. Then we need to set our dev board. There are tons of ESP32 boards to choose from, but ironically, the ESPI is missing from the list. Instead, you can select the ESP32 rover module. Unfortunately, there's a small bug in this example. The ESPI's microphone is wired to the left channel, but the sketch configures the right channel. Luckily, this is super easy to fix. In the loop, we regularly call the inference function, passing in the microphone signal and a result structure. These are then printed out on the serial monitor as confidence scores, just like the ones we saw earlier in the browser. I added this part here. The confidence values are stored in an array. Index 1 corresponds to red and index 3 to white. If either value goes above 0.6, the corresponding LED is turned on while the other is turned off.
White, white, green, green,
Bruh.
yellow, white, white, yellow, unknown, red, white. Okay, sometimes I have to say things twice, but it clearly works.
Of course, you can improve this by recording more samples. I also showed you some parameters you can tweak. By the way, if you don't have an ESPI, you can connect any generic ESP32 dev module with a digital microphone and 2 LEDs, like I did here. I also added the classes light on and light off to the dataset.
Light off, light on.
Then I flashed this light bulb with Tasmata, so we can control it via a REST API and its built-in web server right in your local network, without involving any shady cloud server. With a bit of extra code, I added the Tasmata calls into the sketch. And there we go.
Light on,
An Alexa alternative that won't spy on you.
light off. Thanks, Eric. Great job. And big thanks to all of you who made it this far. See you in the next one.